Hi guys, we're going to be going over the least squares method today. Alright, so the least squares method. So the first thing is we're going to be going over why the least squared method is important. So the main thing is that you're trying to figure out data relationships between two variables so you can model these. So we're doing this and we're looking for trends in the data. So this is taking these data points and creating these fitted lines through those which we can use to model different things. So then with these are important to find those models because then we can interpolate between values and see that. Or if we look at this continued trend line, we could say, hey, at day 60, what do we think cases will be? And then find that point, go over, and let's say it's 2,000. And then we have an estimate for that. All right, so the method that least squares uses is by maximizing the squared or the r squared value. So this is by using residuals, pretty much. So our residuals, if you look up here, is the distance between our fitted value and our observed value. So this is the data point, this is our fitted line. So that is the residual, the distance from our fitted line to there. These can range in any magnitude because we can never tell how far a point's going to be off the line. It can be all the way up here, or it could be down there or something. So we never know, so there is no range for what a residual could be. But we use r squared. So r squared is a little bit different. So to find our r squared value, we use our SR, which is taking our fitted line and just looking at these residuals, and then also taking just the average of the whole y value of the data and looking at the residual from how far they are off the total average. So that's what our ST is. And then just to repeat myself again, the SR is our normal residual, and the ST is the residual from the average of the y value. So then we calculate our r squared, or coefficient of determination, by taking SR, or FT minus SR, and then dividing that by ST. So that's also right here. So this is going to create our r squared value. And because you're dividing by it's ST minus SR divided by ST, these are going to range in value from 0 to 1. So this makes it really easy to determine how good your fit is. So at 0, that means that the line is terribly fitting and it makes no sense to the data. Whereas 1, the data makes perfect sense with the fitted line. So the closer you can get to 1 on your data or on your fitted line, the better. So that means coefficients of determination such as 0.99 are amazing, and that means it's a very good representation of your data. So yesterday I posted the video where I did all the coding for the least squares method of determining a fitted line for the COVID-19 outbreak in North Dakota. So for our fitted equation, we used a quadratic. So we had our x squared, our x, and our a naught. So these a naught, a1, and a2 are just coefficients before our terms here of 1, x, and x squared. But those are not the only things you can model with the least squared value. If you have a periodic data set, you could use sine and cosines. If you have an exponential, you could use e to the x. And you could use an infinite amount of terms, as long as you can just code it up, and just different terms as well, as long as you know what they are. So those number of terms are going to be this m right here, and that's going to be really valuable in sizing the matrices. And then this n is going to be the number of data points. So for us, that's 50 days that we took data from, and our M is 3, our A naught, A1, and A2. All right, now we're going to look, and then here to our right is just a coded version of what the line's going to look like. All right, so this is how you do it with matrices. So the first thing is we're going to have three matrices. We'll look at them right here, Z, Y, and A. So Z is M by N, so the number of terms by the number of data points. Y is N by 1, number of data points by 1. And A is M by 1, so the number of terms by 1. So our Z matrix is going to hold our X values. So like if we look here, this is the coding I used to fill my Z matrix. So we had it had 3 rows, so we had that right there. So our first one, we're just going to fill with 1s for our A naught. So that's just going to give us our intercept, and we'll just fill that with 1s because we know that'll be a constant. Our second column we know is a function of x, so it's a2 times x, so, or a1 times x, sorry, excuse me. So for that, we're going to fill it with the x of I, so our x from our data point. And then following that, we know that a3 is going to be, or our a2 in the third column is going to be our x squared is what it's going to be times. So right here we have our x squared from our data, and then that's going to give us all our data. And here's an example. So for our data, we had 50 terms, but I just did the first 4, so like we'd have 1s for all this row. Then for our x's of i's, we have 1, 2, 3, 4. Then our x of I squared is going to be 1, 4, 9, 16, so on and so on. Now, the next matrix is going to be our Y matrix. So this matrix is going to hold all our Y values from the data set. So this is just 1, 1, 1, 3, so on, so on. And that's represented in this line of code. So that's just taking the raw data and putting it into a vertical matrix. Then I would say most important is our A matrix. So this is what's going to be unknown, and it's going to have our A naught, A1, and A2 value. If we go back, so MATLAB does, or A1, A2, A naught, A1, A2 value. So MATLAB does not have a 0th indices, so we have A1, A2, and A3, and these are equal, they're just in different indices. So then we can solve this by using this. We know Z transpose times Z times A equals Z transpose times Y. So we know what Z is, and then obviously Z transpose, and we know what Y is, because those both come from our raw data set. But we don't know A, that's what we're figuring out for our line. So we reorder this, and we get A is equal to Z transpose times Z times Z transpose times Y. So we can model this up right there using the backslash operator from matrix math. Then once we solve, we're going to get 3 values in this A matrix. So let's say it's 1, 2, and 3. To find our fitted line, we just take that. So we had A1 is equal to 1, we'd put that there. A2 is equal to 2, we'd put that there, and A3 is equal to 3. So we'd put those in, and then we'd end up with our fitted line, y equals 1 plus 2x plus 3x squared. And this is going to go, and this is going to be our fitted line. Like if we go back to this slide, this is this fitted line right there. Let me clean this up so it's a little easier to look at. So our fitted line is going to be our trend line right there, and that's going to come from using these A values and plugging them into our fit equation. All right, that's all I have. Thank you, guys.